going to talk briefly about the code development process. We're going to make sure we have enough time for Dr. Ghosh to speak about the potential workable solutions for functional recovery. What you have on your slide here is a graphic of our process. The international codes are updated every 3 years. The current edition is the 2018. It's an open process. Anybody can submit either code changes, to update the codes, to revise the codes, and public comments, which are a function of after the committee has deliberated and made a decision and passed an action. Our process entails 2 public hearings, emphasis on public, where anybody can participate in the update and the development of our codes. The first hearing is in front of a hearing committee of specialized experts. In the case of structural, obviously the International Building Code Structural Committee. The second hearing is where the vote actually occurs in terms of the final product, whether or not to change the code. And that rests with one entity and one entity only. That's what we call our governmental member voting representatives. Those are the ones involved with only health, safety, and welfare. They have no vested interest other than that in fact. The last step is one of an online vote. And for those folks who cannot participate in our open hearings, we do have an online vote that occurs following the conclusion of our second hearing. Participation in the process is from a wide range of groups, all basically related to stakeholders in the building community. The likes of ASCE, SEI, FEMA, the ATC Seismic Code Support Committee, structural engineers that was already mentioned, the likes of CI, NCSEA, individual structural design firms, construction material associations, obviously the 4 major ones, steel, wood, concrete, and masonry. The IBC relies heavily on reference standards to accomplish the task. The ICODES reference over 1,400 reference standards. Obviously, when you speak of structural, the focus is on ASCE 7, specifically ASCE 7-16, and the likes of the steel manuals, ACI 318, TMS, etc., etc., etc. What's found in the building code is more of the policy side. You're dealing with the risk categories, which are basically an identification of the expected level of performance. Obviously, an agricultural building compared to a hospital, you expect a different level of performance. Hence, the risk categories are different for those different types of buildings. From the risk categories, you utilize the IBC to establish the seismic design category. So in other words, the IBC, relative to seismic design, sets the table for the use of ACI 318, ASCE 7, etc. So with that, I really want the presentation here on the code side to really focus in on workable solutions, and that's where Dr. Ghosh will follow up.
Thank you, Mike. Good morning. I need to see my slides, and we have moved the podium enough that I should be able to do that. I'm supposed to talk about mind-side workable solutions. What I'm starting with is the way we have been doing seismic design for the last number of decades has come under some criticism in recent times. So this is a quick look at what it is that we have been doing. And let me see, the pointer isn't very It doesn't work. Okay, so if you focus on the right-hand line which says risk category 1 or 2, those are the buildings that we design most of the time. Risk category 2 would be all office buildings, apartments, etc. So those buildings are being designed, if you look at the red dot, to not collapse in the maximum considered earthquake, which would be an earthquake that comes every 2,500 years or so. The same building is supposed to be life safe in the design earthquake, which in California would be an earthquake that is likely every 500 years or so. in the east, that would be once every 1500 years maybe. And then in a frequent earthquake, which would be every 50, 70 years, somewhere near that, we are looking for immediate occupancy. So people should be able to move in immediately after the frequent earthquake. Now, if you look at the leftmost line, risk category 4 structures, which are hospitals, police stations, fire stations, etc., those are designed to be life-safe in the maximum considered earthquake. If you move up to design earthquake, they are supposed to provide immediate occupancy after the design earthquake, so people should be able to move in. Does not mean everything works in the building, but it is safe to move into. And then in the frequent earthquake, it will be operational. Everything should be working, or almost everything should be working. Now, the criticism that has come, if I understand it, is that we are not designing risk category 2 buildings like risk category 4 buildings. We are not providing for immediate occupancy after the design earthquake. Now, this is a look at, without a pointer is kind of difficult, but this is a look at if anyone around the world is doing better than we are. So this is damage statistics from the 1985 Kobe earthquake from the Disaster Prevention Research Institute of Kyoto University. On the x-axis is the age of the structure when it was constructed, as you see 71 to 75, 76 to 80, etc. On the y-axis, this is wonderful, thank you so much. That's so much better. So on the, okay, let's, so the yellow is severe damage or collapse. The purple is kind of moderate, it is described, I cannot read from here. The red is kind of minor damage and the green is basically no damage. So older buildings, you see a high percentage is suffering severe damage and a very low percentage is escaping any damage. Now, if you look at the buildings that are vintage 71 onwards, the percent of severe damage has gone down and no damage has come up. Buildings constructed after 1981, there is absolutely no severe damage, and the newest buildings, all of them have escaped damage. So there is correlation between damage and age of the structure. The two milestones are 71 and 81 because after a major earthquake in 68, they made major changes to their building codes in 1971. And after a second earthquake, major earthquake in 78, they made a second change to their building codes in 1981. Structures designed by the 1981 code have done extremely well in all subsequent earthquakes, and there is absolute verification of that. So the 81 change was introducing a two-stage design. They are now designing to essentially prevent, so structural damage should be prevented in events that may occur more than once in the lifetime of the building. And that's an earthquake that comes every 30 to 50 years. They are also designing for protection of human life in a rarer earthquake, and that rarer earthquake comes every, a return period of several hundred years. So no damage in the frequent earthquake and life safety in an earthquake with a return period of several hundred years. Now, so buildings designed by this two-stage procedure, as I have said, have done remarkably well. And if you look into how they are achieving this two-stage solution is by providing more overall stiffness to their buildings than we do. Their buildings are stiffer, they move less in the design earthquake ground motion, and that accounts for the improved performance. Now, functional recovery, as Susan said, the definition has been widely distributed. I put the same definition up on the screen. The only point I wanted to make is, so post-earthquake structural and non-structural capacity are maintained or can be restored to support, etc. The key thing is within a maximum acceptable time that might differ for various uses or occupancies. David Bonovitz here has written what I found to be a very thoughtful paper for the next edition of the NERC provisions resource paper, where he has made the point that this recovery time could be variable depending upon the use category. But if the recovery time is very short, we are talking about immediate occupancy after the design earthquake. If the recovery period is long, then we are probably back to the design that we have been doing over the last few decades. Now, the key, as I said, is more stiffness in our structures. Does it cost more money? If it does, then I do not believe that it is a solution that would be well received by the community. So this slide tells us something that we know, the homeless problem in California, in the big cities, all over the state. Affordable housing is already a problem, so we are definitely not looking for solutions that will increase construction costs or cost of housing in any way. So is there a solution that will give us what we need without costing more money? So in this picture, we are looking at the seismic response of a particular structure to the design earthquake of ASCE 7 or the IDC. So on the x-axis are the forces induced in the structure by the earthquake. On the x-axis are the displacements that the structure suffers in the earthquake. Initially, we are showing elastic response, meaning there is no damage associated with the earthquake response. The earthquake passes, we get the structure back intact, no damage to be repaired. Now, if I turn it, so this elastically responding structure develops a force F sub u in the process of going through the earthquake and suffers a displacement delta sub u. If I turn around and say that we are now required to design this particular structure to respond elastically to this particular earthquake, the immediate conclusion would be we must provide to the structure a strength at least equal to F sub u. If we decide we cannot afford that, all we can afford is a much lower strength level F sub e, then if the design earthquake comes, hits our structure, when the earthquake induced forces equal and then exceed the supply strength level, the structure will start cracking and yielding in places. That will be the beginning of inelastic displacements, which are associated with damage. We will not get our structure back intact following the earthquake. Now, we know based on observations and studies that the total displacement suffered by this inelastically responding structure is about the same as the elastically responding structure. The difference between the two is much of the displacement is now inelastic. That has damage associated with it. This inelastic displacement needs to be within the inelastic deformation capacity of the structure, the inelastic displacement over which gravity loads can be sustained. Inelastic deformability comes from proper detailing of the members and the joints. So if we design for large inelastic displacements, we have to do fancy detailing, which we do by our codes and standards. Now, if we are going for a stiffer solution, if our structure is like this rather than that, the stiffer structure will attract more force to itself. So the seismic response of the stiffer structure will be depicted by this line and that line. The point I'm trying to make is that the inelastic displacement is now much lower than that of the less stiff structure. Okay, so and that should require less fancy detailing, which will save us significant or can save us significant amount of money. So if we go for stiffer solution, the stiffness itself may cost more, but the savings in detailing may very well more than compensate for the extra cost of stiffness. Time is almost over or is over, but I want to throw in a couple more slides to make this point. The point that I'm making is kind of verified. This is a paper from the PCI Journal 1995 that has shown that in earthquakes around the world, structures with concrete shear walls, which are stiff structures, have done extremely well, although the shear walls quite often have been very poorly detailed compared to the way we detail in this country. After the 1985 Chilean earthquake, Sharon Wood wrote a paper, and I would read only the last 3 lines. The buildings in the Viña del Mar and the associated studies of I cannot read the word. Anyway, has demonstrated that building stiffness building stiffness can eliminate the need for stiffness in structural walls. That's the point I want to make. So if the building is stiff, our walls do not have to be detailed in the fancy way that we have been detailing our structures. So the summary of what I'm saying is that if we want to go towards functional recovery, we should be designing stiffer structures. I'm not suggesting that that means always including shear walls. Stiffness can be achieved in many ways. And if we go for stiffer structures, we should get away from our attachment to fancy detailing, which has become almost an addiction now. We should re-examine the very fancy detailing we are doing, and that has the potential of saving significant money, which will probably more than pay for the stiffness that we need. Thank you very much.